Now, in this course experiment physics 2, basically we will discuss the optics experiment as well as some experiment on quantum physics. Okay. So, what type of what we expect about the optics laboratory, how it should be. So, let me tell you how it should be and what are the basic components should be in the laboratory. So, in optics laboratory, this laboratory should be in a room from which all external light can be excluded. Okay. So, in that room there should be provision, it may not be completely dark room, but there should be provision for preventing the light coming from the outside, external light. Okay. So, that arrangement should be there in optics laboratory. And in optics laboratory, most useful component, that is basically optical bench with slot and millimeter scale, and this optical bench should be supported on feet that can be varied in height to level it. Okay. So, in optics experiment, leveling of the component is very important, because you know that reflection, refraction, mainly everything is a light, it is related with the reflection, refraction, some other phenomena also there. So, if mirror is slightly tilted or so light will go in different directions. So, to get the light in a proper direction, so alignment of the optical components are very, very important, and that is the difficult part in the optics experiment. So, one has to do very carefully and step by step, there are some rules, so one has to follow, and then it will be comparatively easier. Okay. So, there should be optical bench in the laboratory, and that bench should be using the spirit level, that bench first initially that bench should be leveled horizontal. Okay. So, to make it horizontal, because this bench you are putting on a table. So, this table may not be the perfectly, the surface is not perfectly the horizontal. So, you should not defend on the table. So, this your optical bench should have provision to adjust the height. So, that is why this optical bench have feet. It is the basically screw. It put on basically always on 3 screw. Okay. So, you can just rotating the screw, you can change the height of the one end or other end of the table or bench. So, putting the this what is called this spirit level. So, you have to first make the optical bench horizontal. Okay. So, that is very important. So, there should be optical bench, and there should be millimeter scale. We generally tell this meter scale attached with this optical bench, and there should be height adjustment for the for the bench, okay. Height adjustment option for the bench for leveling it. So, then essential accessories to the bench. So, for this on the bench, okay, accessories, necessary essential accessories are several holders, okay, several holders. Okay. So, these holders will put on the slot of the optical bench, and this holder can translate, we can move the holder along the slot, okay, along the slot, and also this holder, it is a we tell also upright. Okay. So, this holder will have option to hold some optical component on it. Okay. So, several holders with 2 degrees of rotational freedom and 2 degrees of translational freedom. So, along the slot you can move that one. Apart from that, this holder should have 2 more translational freedom. So, one is height adjustment, and another is in perpendicular to the slot or optical bench, you can move this holder. Okay. So, minimum 2 degrees of freedom you need, one is height adjustment and another is perpendicular to the slot, and third one is all the time it is there. So, you can move towards the along the slots. Okay. And two rotational freedom means this holder you can rotate, tilt along this or along this. Okay. So, because optical component will be attached with that. Okay. So, that optical component we have to make vertical, there should not be any tilt, etcetera. So, to adjust this those things. So, this holder should have rotational and translational degrees of freedom. Okay. These are very important, otherwise it become very difficult to align the optical component for different experiment. Okay. So, also this holder should have index mark or pointer to measure the displacement on the scale. Okay. So, optical table have scale, right, optical table have scale. So, you are putting the these holders on this on the in the slot of the optical bench. So, now this holder should have a marker, okay, should have a marker or one mark or index. Okay. In the middle position, actually this whatever component you will put on this holder. So, depending on the position of the component on the holder. So, exactly on the base of the holder. So, there will be a mark. Okay. So, that mark or pointer actually will be used to read the position of the holder on the optical bench. Okay. So, these the essential accessories for the bench. Okay. Apart from that, in the laboratory there should be common components that anytime you may need those components. Okay. For optical experiment, that is the those are basically mirrors. So, you should have there should be several mirrors, plane mirrors, concave mirror, convex mirror, lenses, concave lenses, convex lenses, then telescope with crosswire, eyepiece, I think eyepiece with eyepiece, then collimator with variable slit. Okay. If milky glass skin, white skin basically, okay, to see the real image, pinhole, okay, sharp needles, laser source, incandescent source, etc., with proper arrangement for placing them in holders of the optical bench. Okay. So, so these are the very common components for the optical lab: mirrors, lens, telescope, eyepiece, collimator, okay, screen, okay, this pinhole, needles, laser, some optical source. So, laser source, some other bulb source, okay, or discharge source. Okay. So, only these are not enough. Now, this there should be proper arrangement to put them on the holder, which will be used on optical bench. Okay. So, so these arrangement are very essential. Without them, it is very difficult to do the experiment, because it will be time consuming to align them. If you have proper holder and then this some good arrangement to hold the components, okay, and with some rotational, translational freedom of the holder, then comparatively it will be easy, and you can save your time to do the experiment. Okay. So, these are the very common components in the laboratory. So, then you need basically different light source. Okay. Generally this sodium light source, mercury, helium light source, neon, these are the sources we use in our teaching laboratory. Okay. Then you need prism spectrometer, travelling microscope, prism, grating, slit, polarizer, photodetector, etc. It should be stored in the laboratory. These are whatever. So, this optics laboratory should be like this. So, whatever I told here, so these are the very basic components. It is not for a it is not that this for a particular experiment whatever need that is only there. Okay. So, there should be these are the just is like consumable components. Okay. It is like just like screw and nut bolt, okay, screwdriver kind of things. So, in optics lab, so these are the this kind of things. So, anytimes you may need any components. So, it should be stored in the laboratory, optics laboratory. Okay. So, and for different experiment you need different things. So, so that is different story, but whenever you will go to optics laboratory, so this should be the environment of the laboratory. Okay. So, whatever components I told you here, whatever things I told you, everything I will show you in laboratory. When we will do some experiment, and every components I will show you in laboratory, and also I will discuss how it works. So, here what I will not discuss there, I will not discuss about the light source there, but light source is one of the component, one of the important component for optics experiment. So, now I will discuss about the light source here. So, rest of the about the components I will discuss in the laboratory during the experiment. Okay. So, that is what I told, this time to time I will show all the components in the laboratory and discuss the function of them before performing experiment for a particular objective. Okay. So, light source in laboratory, it is basically electromagnetic wave in visible range. Okay. That is what light we tell, although electromagnetic wave have a different range. Okay. So, but visible range that we tell it is light, which will be basically used in the laboratory in teaching lab especially. Okay. So, in the visible range, so we will get different color basically. So, this red color, so this wavelength range, when wavelength range of electromagnetic wave is it is approximately 6 to 800, 6 to 800. So, in that range we tell red, then this side is around 600, that side orange we tell this color is orange. Then this yellow color generally is the 550 to 600 is a yellow color, green color 500 to 550 in that range green color. This range is not, is roughly I mentioned here. Blue color 450 to 500. So, there is a blue color, violet color that is 400 to 450, that is the violet color. Okay. So, there are range of this wavelength. So, for different source you will get different color and their wavelength are fixed. Okay. So, their wavelength are fixed, that red color same color, okay, but wavelength for some source it will be 680, some source it may be 700. Okay. Similarly, for other color also same. So, color will not tell the wavelength, it will tell the range of the wavelength. Okay. But for a particular source, that color light of a particular color, okay, will have a particular wavelength. Okay. So, how we get the light? So, basically there are two ways, this light source that emit continuous wavelength, and there are light source that emits line spectra, okay, discrete wavelength. Okay. So, in our laboratory we will use light which are basically emit line spectra or discrete wavelength of light. Okay. So, for light source that emits line spectra, so that when we get this type of source, when matter is excited through heat or electricity in its gaseous state, spectral lines of different colors are emitted. Okay. So, this is basically an atomic event and the spectral line is unique for each atom in periodic table. Okay. So, this discrete color we are getting, lines we are getting, lights of discrete wavelength we are getting, that is basically atomic phenomena. And as I mentioned that each atom in the periodic table have a characteristics light. Okay. That means it has fixed wavelength. Okay. So, that is why for light for different wavelength, if you want, so you need to use different source. Okay. So, So, let me just tell you what are the source we are using in the lab or we will use in the lab during our experiment. So, we will use hydrogen source, we will have hydrogen source this atom. So, so how is it's I have used this example first because you are quite familiar with this hydrogen energy levels, right. So, from Bohr theory, okay, you know this 1 by lambda wave number equal to z square r 1 by n 1 square minus 1 by n 2 square. So, this is the hydrogen or hydrogen like atom, okay, means in that atom or ion only one electron are there, other electrons are removed. So, for hydrogen it is a z equal to 1. Okay. So, n are principal quantum number, r is the Rydberg constant, it has some value. Okay. So, n equal to 1, 2, 3, these are the energy levels, right, for hydrogen. Now, in hydrogen 1 electrons are there, when either heating or through electricity, if we excite these hydrogen atoms, hydrogen gas. Okay. So, the electrons generally it is in ground state, it goes to the higher energy states, and now in higher energy states is the it stay only very small time. So, generally 10 to the minus 8 second, okay, and then it jump back to the lower energy state. Okay. So, when it jump to the lower energy state, so from heating or from electricity it gain energy and goes to the higher energy levels. When it jump to the lower energy levels, so the energy difference between these two levels, okay, so that energy actually comes out as a electromagnetic wave. Okay. Now, when that wave is in the visible range, so then we see the we see as a light, and that light what will be the color. So, that will be decided from this wavelength, right. So, in case of hydrogen there are different series. So, you know this Balmer series in the Balmer series is in the visible range. Okay. So, if we use hydrogen source in laboratory, when we will use hydrogen source, so in hydrogen source whatever light will come out and that light we will use for our experiment, and there this you will see this type of line spectra. So, one line you will see these are red color, you will see that is the 6.3 nanometer. So, these are basically from the handbook. Okay. You will get this this value of the wavelength of this line spectra. So, generally these are there are other lines also. Okay. Maybe not for this source, for other source, okay, but all lines are not intense. Okay. There are weak lines, there are strong lines, there are medium lines. Okay. So, so here for hydrogen, so this typical wavelength of light we will get. So, this is the 56.3 nanometer, then 486.1. So, these are not the color exactly. So, yeah, maybe it is because I did not have all sorts of color. So, I had 4 colors. So, I try to just adjust with them. So, 486.1 nanometer, another line you will get 434.0 nanometer, other one 410.2 nanometer. So, these are the basically prominent lines, prominent intense light you will get of this wavelength. Okay. So, this source we use in our laboratory, then second source we use in our laboratory, that is sodium source, that is sodium source. Okay. So, for sodium source again this 11, it atomic number is 11. So, it is the this last electron, it is on 3 s 1. So, these are field shell. Okay. So, this electron generally it is excited to the higher energy state and higher energy state, okay, and it produce the light. Okay. So, n equal to 3, this n equal to 3, n equal to 4, n equal to 5, okay, these are energy levels. Now, it is n equal to 3, L equal to 0, 1, 2 means SPD. So, it has 3 sub level SPD, no 4 sub level, I think 0, 1, 2, yes 3 sub level SPD, not F, I think I did mistake, not F, SPD. Okay. So, this in case of hydrogen this was not there, this was not there, or it was there, but they had same energy, it is a degenerate states. So, in this case their degeneracies are removed due to presence of the other electrons. In case of hydrogen it was not there. So, in presence of other electrons, so basically due to the interaction or effect of the other electrons, so these degeneracy are removed. Now, there are spin orbit coupling, LS coupling, spin orbit coupling, okay, gives J value. So, again they are splitted, okay, again they are splitted. So, for S L equal to 0 and then spin half. So, J is half, J is half. So, 3 S half, this state is called 3 S half, and P L equal to 1 and S equal to half. So, J will be L plus half, L minus half. So, P half and P 3 by 2, and these 3 basically principal quantum number. Okay. So, there are others also. Okay. So, in case of sodium we get basically these two lines in the visible range. There are other transitions, but they are not in visible range, we cannot see, we only see this, these two spectral lines. So, the wavelength is 5890 and 5896. So, 6 angstrom difference between these two light. Okay. So, in generally we see them as a one line. Okay. It is very difficult to resolve them. Okay. Even through prism, ordinary prism we cannot resolve them, we will see only one line. So, that is why we tell it is a monochromatic source YOLO, and this is in the range of 550 to 600. Okay. So, this is the range of yellow color. Okay. So, this sodium yellow color light we see, that we tell D line, and this we tell sodium doublet, because it has 2 line D 1 and D 2 line, and wavelength is 5890 and 5896. So, average wavelength we consider when we do not see this doublet. As I told, these differences are very small, only with high resolve spectrometer you can resolve them, otherwise in ordinary spectrometer you can see only one line, and average wavelength we take 5893. Okay. So, this sodium source is a very essential source, all the time we need this source, and we will use them. So, that is why I discuss what is the origin of them. Then helium source, that is also we will use this for helium source. So, again this atomic transition. Okay. So, from lower level to higher level, the electron goes absorbing the heat energy or the electrical energy, and then immediately it come to the lower level and gives the spectral lines. Okay. Whatever the principle for hydrogen I have discussed, or sodium I have discussed, for this also same principle. Okay. So, number of electrons are more things to exactly find out this transition is slightly difficult, but we are not going to that only we learned that this is the atomic transition. Okay. Due to the transition of electrons from one level to another level, we are getting this light. Okay. And these are the characteristics of that source, whatever the light we are getting. So, that is the characteristics of the source. So, helium source also we will use in our laboratory, and this type of spectra you will get, and you will get these are the wavelengths. Okay. These are the wavelengths, and these have strong intensity, and these have although it is the medium intensity, there are more and their intensity are very weak. Okay. And then mercury source also we will use in our laboratory. There you will get light of this wavelength, Okay. So, and here also again there are some other lines, weak lines, is difficult to see them. So, generally, but these lines are prominent. Okay. And then another source we use in the laboratory, the neon source, and for neon source you will get a lot of lines in the range of 600 to 700 wavelength. Okay. So, all are more or less red color, and this side it will be orange color. Then we get two lines, the yellow color, but there is the doublet basically. Wherever you are getting doublet, so that is basically it comes due to spin orbit interaction. Due to the spin orbit interaction, whatever the splitting of the energy level, because of their that generally we get this doublet structure. They are very close, they have very close wavelength. Okay. And very prominent green color we see for neon source. So, from the color itself and from the data table, you can say what is the wavelength of this. Also, we can measure the wavelength, that is what experiment we will do using the defined source, how to measure the wavelength of that source. Okay. So, also we use in the laboratory, that is laser. Okay. Generally helium neon laser, its wavelength is 632.8 nanometer, helium neon laser. So, that we will use in our laboratory for some experiment. Okay. And its intensity is expressed in terms of watt, okay, wavelength as well as watt of different, for different intensity is defined as a different watt. Okay. Also we will use diode laser. So, different diode lasers are available of different wavelength. Okay. So, there are various kind of wavelength, various kind of lasers, and they have various kind of wavelength. Okay. So, what are the advantage of laser source? Laser source, you know, light amplification by stimulated emission of radiation. How it works, I am not going to discuss, but it has unique property, you know. So, it is a nearly monochromatic, it is nearly monochromatic, it is a high directional, this laser source is highly directional, and it is a highly coherence. It is a, what is coherence, I will explain when I will do the interference experiment. Okay. So, these are the unique property of the laser light. So, that is why laser light in our laboratory, just for in some experiment we will use laser light, but for other high end experiment for research laboratory, this without laser we cannot think. Okay. So, there are a lot of application for doing the experiment in research laboratory. We use different kind of lasers. So, if you see the action function of the laser, how we get the lasing light. So, that is basically we tell atomic laser, it is a gas laser as helium neon laser as I told. Otherwise, this other visible and ultraviolet argon ion laser, helium cadmium laser, then green and yellow color, yellow copper vapor laser, means we get the green and yellow color from these lasers. Okay. So, these are the basically gives monochromatic, means one wavelength laser, these are one wavelength laser. Okay. So, this wavelength are fixed for this laser, only intensity we can vary for different watt. Okay. Then molecular laser, it is also gas laser, carbon dioxide laser, then excimer laser, okay, pulse nitrogen lasers. So, these lasers we will not use, these are used for specific purpose for higher end experiment in research laboratory. Just I am mentioning here some liquid lasers are there, dielectric solid lasers are there, molybdenum doped this YAG. YAG is basically yttrium aluminum garment, okay, or to molybdenum doped glass laser. So, these are the different kind of laser, and this we use in our laboratory, not for teaching laboratory, for other purpose. Also semiconductor laser, it is made of basically gallium arsenide, indium phosphide with various mixture of impurities. Okay. So, these are the briefly I told about the light source for visible range we will use in laboratory, and some of them we use in our research laboratory, just I mention them here. Okay. So, about other components I will discuss in the during the experiment in the laboratory. Okay. So, I will stop here. Thank you.